So last time we looked at the development of these equations. These are our nonlinear system of equations that are really our equations of motion. And remember, the top six equations here are Newton's second law, and then the bottom six equations are what we call the kinematic transformation equations that tell us how we're changing in XYZ on the Earth and how our orientation is changing as a function of time. So now we want to use these equations to study the dynamics of an aircraft. And the current state of these equations is rather complex. They're nonlinear, and it's very difficult to see anything in these equations because of their complexity. So what we're going to do is to learn more about the dynamics of an aircraft. We're actually going to linearize these equations. Okay, now this step can be a little bit confusing to students, and so I'm going to take some time here to walk through the basics of what's going on at a more fundamental level, and so we're actually going to come back to these equations in just a little while later when we're ready to linearize these actual equations. And instead, I'm going to walk you through what's called small disturbance theory. Okay, small disturbance theory is what we're going to use to linearize these equations, and it's a very common methodology for simplifying a very complex problem to understand the real fundamentals of what's going on. Okay, so we're going to walk through this in kind of a theoretical approach here, and then we're going to show a really simple example. So hopefully this simplified example is going to make a lot of sense to you, and then hopefully at that point when we come back to these equations to apply it in a more to these particular set of equations, then you'll be able to see your way through the problem a lot better. Okay, so let's talk about small disturbance theory. So in general, what we're doing with small disturbance theory is we're saying that we know we're going to start with some known solution, okay? So we're going to call this y as a function of a bunch of parameters. So, that could be a, b, c, and we could have as many parameters here. We know some solution to this problem, and so I'm actually, the known solution, I'm going to subscript here with a sub O. So that means that we have some known solution, and we're going to say that the general solution, y, as a function of all of these parameters, and more parameters there, the general solution we can estimate by knowing a known solution and then adding some perturbation or some small disturbance to that known solution. So we want to estimate. So let's say that this is the general solution here, and it's a function of all those things. Well, when we plug in a, b, c, or d, or whatever, we're going to get some perturbation relative to this known solution. Okay, so some deviation relative to that, and hopefully it's going to be close though to the known solution. And so we can actually use this method of small disturbances to linearize the solution and estimate what the exact solution would be as just a deviation basically from a known solution. Okay, so this probably is feeling a little bit theoretical. Let's walk through some math to show you the methodology here, and then, like I said, we'll go through an example. Okay, so we start out with just our general solution. So this is our general solution, is y as a function of some parameters, a list of parameters, and we have a known solution that is y naught. So we know the solution at one set of these parameters, which we're going to call a naught, b naught, c naught, and so those are our known. That's our known solution. And now we can say the general solution, y, can be estimated from a Taylor series expansion about the known solution. So it would be equal to y naught plus the change in y with respect to the first parameter, a, that would be evaluated at the known solution, by the way, is also called the particular solution. Okay, so we have one particular solution. So that is, we're going to evaluate the derivative of y with respect to a at the particular solution. Okay, so I'm just going to put part there. And then we'd multiply that by my real value of a minus a naught, so a deviation in a. Okay, so we're going to take the first derivative multiplied by the change in a. And then we could do the same for every single parameter there. So also the partial derivative with respect to b evaluated at the particular solution, or that known solution, multiplied by b minus b naught, and we could keep going. Now, I've only written down the first order terms in this Taylor series expansion, but you can certainly have higher order terms as well. So after we fill out all these different variables, then we can go to higher order terms of those variables. And so this is just a Taylor series. You should be familiar with that. Okay, so at this point now we can rewrite. We can say that let's just rewrite this here first. So y equals y naught, my known solution, plus partial with y with respect to a evaluated at the particular solution times, we're going to call this delta a. And actually, let me back up here. I think I'm just going to, I'm also going to move this stuff on the right-hand side and say that our delta y, so if you take this y naught and subtract it over to the other side, we're going to get y minus y naught equals what we're going to call our delta y. Okay, so this is a deviation in that solution is equal to now the first derivative of that solution with respect to a at the particular solution multiplied by delta a plus the partial of y with respect to b at the particular solution multiplied by delta b. And of course, you can add more terms here and higher order terms. So what we generally end up doing is to linearize this system, we're gonna drop the higher order terms here, and so we're just going to include the first derivative of the solution with respect to each of these input variables. Okay, and so that gives us a linear equation here. So so this is our final version for the solution, or our deviation in the solution relative to our known solution or the particular solution. Okay, so this may still feel a little bit abstract. So let's do an example here about something that should be pretty straightforward and obvious, hopefully. So let's look at the area of a rectangle. Okay, so here we've got a rectangle, and we're going to call this the height and the width. And the total area here is equal to, so our real equation here is height times width, okay? That's the area of that rectangle. Well, let's say that we know one of these solutions. We know some A naught equals H naught times W naught. So we know the solution for a particular rectangle. So we know the particular solution for that, and what we want to find is a general solution. Well, this general solution, this equation is so simple. Of course, we would just solve it, right? We could plug in any H or W and solve for the general solution. But let's pretend like that equation was so complicated that that it was just a little bit more challenging to solve that, and so we didn't want to solve it that way. We wanted to estimate it using this method that we've shown up here. Okay, so what we would do is say our general solution is equal to our particular solution, A naught, plus the change in area with respect to height, for example, evaluated at the particular solution, times delta H, plus the change in area with respect to width evaluated at the particular solution, times delta W. Okay, so all we've done is use this equation to figure out what our general solution to area would be, and this really is just an estimate for what that area is. We're just including the first order terms here. Okay. Okay, so let's plug this in and see what we would get. So that means that delta A, my change in area, if I subtract A naught over to A, would be equal to the first derivative of the area with respect to H evaluated at the particular solution. So let's look at that. So here's our equation up here. The first derivative of area with respect to H is just W, right? So that's just W. And when we evaluate that at the particular solution, that's W naught. And then that gets multiplied by delta H. And now the second term here, the first derivative of area with respect to W, if we take the derivative here of our original equation with respect to W, we get H. So we have plus H, but we're going to evaluate that at the particular solution. So that's actually H naught times delta W. Okay, so this is our estimate for our change in area. Okay, so let's see what that means on our rectangle over here. Let's just try to get a physical meaning for what's going on. And actually, I'm just gonna enlarge this a little bit. So we've got a larger rectangle over here. And here's our height and width. Okay, so our delta area equation here says that it would be W naught, and by the way, this is going to be our particular solution. So we know some A naught at H naught and W naught, and now we want to find in general what is the area of another rectangle. And what we've done here is we've said that the change in area would be W naught times delta H naught. So this would be like a delta H. And over here would be a delta W, if we're going to add that. And the change in area, so if you look at this equation here, what it's saying is the change in area is going to be W naught times delta H. So we've got W naught there, that length, times delta H. So it's going to be this area here. Plus H naught, this height, times the delta W. So we can fill that in here. So so that would be the estimated delta A is all of this area here. That's the linearized estimate for the total area. Now you can see that that's actually not a bad estimate, right? It's not exactly right because we missed this second order term over here. This would be delta W times delta H. So really, the exact solution would have this delta W times a delta H over here. But that's a nonlinear term. When we linearize this, we dropped that term there. And so when we estimate our change in area here, we're going to end up neglecting this little square over here, right? Which isn't a horrible approximation. Of course, it's not going to be exact, but actually what we've captured are the most prominent effects on the change in that the area of that rectangle. Now, again, if you wanted to solve this equation, this is a very simple example, and so solving this equation is not difficult, right? But what I'm trying to show here is just this simple process of linearization. Okay. Now, I want to show a slightly different approach here that we could use for this particular rectangle example. So let me just put over here another approach. And another approach to the same problem, which would give us the same solution, is to say that that our general solution area is equal to, so it's really H times W, but I'm going to write H as H naught plus a delta H, right? So our actual general solution here for the height is going to be h naught plus a delta h. Okay, so I'm plugging that in here, and I'm sorry, I'm using this equation right here, so I'm plugging this right in here. So in general, our area is equal to the height, which I'm going to write as h naught plus delta h, times the width, which I'm going to write as some known width plus a delta width. Okay, so that's my correct equation for this. And if I just factor this out, what I'm going to get is a h naught times w naught plus h naught times delta w plus delta h times w naught, and then plus delta h times delta w. Okay, so so this is equal to, so my general area is equal to a naught. See, this term right here is h naught times w naught, so that's just a naught, plus an h naught times delta w plus delta h times w naught. And actually, these terms are identical to what I got over here. And then this last term right here is what we're going to drop. That's called a nonlinear term. And from small disturbance theory, anytime you have a small disturbance multiplied by another small disturbance, you drop that. That's this nonlinear term that you can drop. We're basically saying that something really small multiplied by something else that's really small is something that's extremely small when compared to these other terms. So, for example, these two terms are much larger than these two terms here, and these two terms are multiplied together. So when you multiply these two together, they're a lot smaller than these, and so we're going to drop those in this development. And so you end up with this exact same equation. So these two are equal. Okay. So that's another way to look at it. And actually, this is the approach that we're going to take now in applying. Well, it's really a mixture of both of these, but I wanted you to see both of these approaches so that you can understand what we're going to do now. So we're gonna now go back to these general equations, which are much more complicated than the area of a rectangular, right? And we're now going to apply this idea of small disturbance theory to understand the dynamics of an aircraft. And just to give you a taste of what we're going to do, the particular solution that we're going to look at is some aircraft in steady level flight. Okay, so we're just going to look at where we've got the balance of forces on this is going to be very simplified. We're going to look at steady level flight. We're going to pretend like this is trimmed for steady level flight. And so our particular solution, our known solution, is very simple, actually, because we don't have any rotation rates, for example. So if I were just to point these out, like these PQR terms that are showing up all through here are all going to be zero. So all of these PQR 0, PQR 0. So a lot of these terms drop out, and so this system of equations simplifies significantly. And that we're going to start there from our known solution, and then we're going to look at the general solution, where we look at all of this stuff, how the general solution is going to deviate from that steady level flight condition based off of the properties of the aircraft.